topic from module 2, that is AC fundamental. So we have studied how to generate the alternating voltage, single phase sinusoidal voltage generation, both the graphical representation as well as the mathematical derivations is E equals to Em sin omega t was discussed in the class. Few terminologies like time period, frequency, average value were discussed in the last class. Okay, so today I'll be starting from this one, the average value of the sinusoidal voltage, right? So previously we have seen, we considered the complete cycle, that is 2 pi radian as time period. What we will get? We'll get the average voltage, E average equals to 0. If you consider the full cycle of the signal as the total time here in this integration. Because of the even symmetry of both the halves, the positive half symmetry will be exactly cancelled out by the negative half side. So the average value will be coming as 0. So in order to avoid this average value equals to 0, what we will do, we'll consider only the positive half cycle for the calculation of this E average. Fine. Just to avoid the 0 average value, because sometimes we need average value calculation for a sinusoidal voltage. Okay, in that case, if we consider average value equals to 0, then there may be some problem in the further calculations. So we'll consider the half time period for the integration. So here, instead of taking t, we'll consider t by 2 for the calculation of E average. So now E average is equals to 1 by t by 2 and equals 0 to t by 2 E dt. What is E? E is Em sin omega t. Em sin omega t, this one. Either Em sin omega t or Em sin 2 pi by t. So with this expression, we'll get E average as minus Em by pi into cosine 2 pi into t by 2t minus cos 0. Right? So if you go through the further derivation, what you will get, you will see that E average is 2En by pi. That means average value, average voltage of a pure sinusoidal wave can be calculated by the half-time period, and it is evaluated as 0.6378. So this expression is very much required in electrical engineering for further calculation, for further analysis of AC circuit or electrical circuit. E average 0.637 of Em. Just remember this expression. The relationship between average value and the maximum value of the pure sinusoidal signal. This Em is nothing but the peak value of the AC signal. Peak value or the maximum value voltage. This one. This is Em. Here, our next topic is root mean square value of a signal. Previously, we have seen the average value. Now we'll see just a minute. mean square value of a signal. What is it? It is the RMS value or the effective value of a signal, which is indicating actually the total heating capacity of the circuit. Now, this RMS value of a signal or the effective value of a signal will be valid only for a alternating voltage or current. It is not required in case of DC circuit. It is only required in case of AC circuit. What does it mean? The root mean square value of a signal. It is just equivalent to the steady DC value of the signal, which gives the same effect. What type of effect? Heating effect. Like you are passing a DC current, current through a DC circuit, whatever heating effect I square R you will be uh, having for that circuit, that will be exactly same in case of AC circuit, in which current flowing through the element which is in RMS form. That means the RMS value of any AC quantity, either voltage or current, will give the same effect, the same equivalent heating effect as that is produced by the DC current flowing through some other circuit over a same period of time. And as the name implies, square root of the signal means square root of the average of the squared values. Like you want to measure the RMS value of the signal from 0 to 5 seconds, which you have taken last day for the calculation of average value. Here today we'll consider the same signal for simplicity. Let's see what is the value of RMS voltage. For example, if xt is the voltage function, so this signal is varying. See, the magnitude is varying, and we know how to calculate the average value. We'll calculate the area of this signal covered by this envelope. Now here, instead of taking uh, simple magnitude, the constant magnitude 4, we'll consider the square of that magnitude, because we would like to determine the same heating effect. Heating effect means total joules, that is I square R. Okay, so here we'll consider the square terms. 4 square into the time period plus 6 square into the time period plus 3 square into the time period plus 8 square into the time period for that interval. That is 4 minus 3, 3 minus 2, 2 minus 1 respectively. And lastly, it is 5 square. Magnitude is 5, so 5 square into 5 minus 4. That is 1. Okay, divided by the total time period, that is 5. And the whole thing will be under root. That's why the name root mean square. That means first we are just starting from this right hand side. First we'll do the square, then we'll take the mean, and then we'll do the root. That's why the name root means square. So for the same signal, the RMS value is something different. It is 5.48. Okay. Now previously, what was the average value? 5.2. Okay. The X average for the same signal, X average was 5.2, but RMS value is 5.48. Just keep this in mind that RMS is higher than the average. So mathematically, how do you express RMS value of a periodic signal xt over a complete one cycle? It will be calculated as square root 1 by t integral 0 to t xt square into dt for is pure sinusoidal wave, whose mathematical expression is Em sine 2 pi by t over a complete cycle, will consider the full time period as the total time. So in case of average, for a periodic signal like sinusoidal signal, we consider the half time period, but for RMS value, we'll consider the total time period, that is capital T. So it is simply square root 1 by t integral 0 to t e squared dt. What is E? E is the periodic signal, that is the voltage of the sinusoidal signal, the sinusoidal voltage expressed as Em sine omega t. So just put E equals to Em sine omega t. Omega is the angular frequency in rad per second, which is 2 pi by t. So after doing this calculation, what we'll get? We'll get E RMS equals to 707 Em. Okay. Can you do this integration, student? So I will skip the detailed derivation. It's a simple integration. So E RMS is nothing but Em by root 2. Maximum voltage by root 2. It is 0.707 of Em. And what was the generalized expression of average value of a sinusoidal signal? It was 0.637 of Em. Can you remember that? Average value of a sinusoidal signal is 0.637 of Em. This one. Where Em is the maximum voltage. And in case of RMS value, it is 0.707 times of Em. So it is just the peak value divided by root 2. Peak value divided by root 2. Okay. Now let's see what is the significance of this RMS AC in practice. Suppose a lamp connected to a 6 volt RMS AC supply will shine with the same brightness when it is connected to a steady 6 volt DC supply. Okay, as I said earlier, that what is the effect of RMS AC? The RMS value is that quantity which will produce the same heating effect as produced by the same DC quantity for a same period of time. That means 6 volt RMS AC connected with a lamp will give the brightness which is exactly same with the lamp connected to a 6 volt DC. But the lamp will be dimmer if connected to a 6 volt peak AC supply because the RMS value of this is only 4.2 volt. 6 volt peak. What is the RMS? RMS is peak by root 2. So 6 by root 2 is 4.2 volt. So 4.2 volt is equivalent to the steady 4.2 volt DC. Okay. Now all the AC voltmeters and ammeters show the RMS value of the voltage or current. This is to be noted. A very important point. All the voltmeters and ammeters show the RMS value, and DC meters can also show the RMS value, but in that case, DC must be varying for a short period of time at least. If DC is varying by some means for a short period of time, then the DC meter uh, can show RMS value. Otherwise, all voltmeters and ammeters will show the RMS value of AC quantity. Next, come to the peak factor and form factor. These two are very important terminologies in AC signal, in AC circuit analysis. Any signal can be represented, any circuit behavior can be represented in terms of the peak factor and form factor. We'll see that later on, how these two factors will be implementing in any AC circuit. Now let's see the definition. What is the definition of peak factor of alternating waveform? It is just the maximum value divided by the RMS value of the signal. That means Em by 0.707 times Em. Kp. Mainly it is denoted by Kp. The peak factor Kp can be expressed as the maximum voltage divided by the RMS voltage. So it's simply root 2 because these two m's will be cancelled out. So it's root 2. Root 2 means 1.414. So peak factor of an alternating waveform can be equal to 1.414. So it is just indicating how much maximum value of a signal can reach for a given effective value. This is the basic definition of the peak factor. Okay. Now, what is the form factor? Form factor may be denoted as Kf. It is the ratio of the RMS value of the signal and the average value of the same signal. So what is the RMS value of a sinusoidal waveform? It is Em by root 2. And what is the average value? It is 2 Em by pi. That means the numerator is 0.707 times Em, the denominator is 0.637 of Em. Em will be cancelled out. So calculate 0.707 by 0.637. It is simply equals to 1.11. So form factor of a sinusoidal waveform is equals to 1.11. Okay. Next one is the crest factor. Just look at these graphical responses showing two signals. One is the pure sinusoidal signal marked by blue color, and the other one is marked with red color, which is not sinusoidal signal. Okay, so you can see the what is the peak value of the red signal. It is around 20. uh, exact y-axis is showing the current. It's a current versus time graph. So maximum current or the peak current for the second wave is around 20 ampere, and for the first one marked by blue color, see its peak value is around 7.5 ampere. So peak values are different. That means current waveforms are different for these two different signals because two different loads are connected with the circuit. So we'll get two different current signals. Fine. Now both have an RMS current of 5 ampere. What is crest factor? Crest factor is the ratio of the peak current by the RMS current. Peak current by the RMS current. Okay. So crest factor will be calculated as 1.414 for the sinusoidal waveform, for the blue colored waveform, because the peak one is 0.707 and RMS current is given in this case, that is 5 ampere. For the second case, for the non-sinusoidal type waveform, see, the peak is around 20 or 21.21. They have taken 21.21 here. So crest factor will be calculated as 21.21 divided by the RMS current, that is 5 ampere. So it's 4.24. So crest factor for the sinusoidal one is 1.41, and for the second one, for the non-sinusoidal current, it is 4.24. That means crest factors are different. Though it is the ratio of the peak current by the RMS current, and though the two signals are having the same RMS current, but since the peak currents are changing, so crest factor will be also changing. Okay. Now, any question up to this? Okay. Let's see the significance of the form factor. It is called as a figure of merit in electrical rectification circuit. Rectification circuit means AC to DC conversion. When we convert AC signal into the DC signal, what we do actually, the we use the rectifier unit. Any type of rectification circuit can be used there, and our major objective is to get the pure DC from the rectifier. That means ripple free AC. Ripple free DC. So, as much as possible, we would like to maintain the constant DC signal at the output side of the rectifier. Okay, so the RMS value of the output waveform will be the same as the average value, and form factor will be 1. Okay, constant. Constant signal means the DC signal. So, what will be the RMS value? RMS value will be the same, which is equal to the average value of the signal for a constant signal. So form factor will be 1. That's why square wave always have unity form factor. Any variation of form factor from this unity is a deviation from the desired ideality. Okay. So for example, if you consider square waves for rectification, will have a form factor F of unity, denoting complete absence of ripples. While sinusoidal waves on rectification will have a form factor of about 1.1107 or 1.11, denoting the presence of unwanted ripples. Now let us see one example, one problem. An AC current expressed as I equals to 14.14 sine 314t. Determine its RMS value, its frequency, its instantaneous value at t equals to 2 milliseconds. That means the current signal is known to us. The mathematical expression of this current signal is given in the problem. So first we'll check the frequency. Can anyone tell me how to calculate the frequency of a signal whose mathematical expression is given?
314 by 2 pi.
Okay, so this 314 is nothing but omega, the angular frequency, because we express alternating voltage or current signal as either Vm sin omega t or by Im sin omega t respectively. This is a current signal, so definitely this will be Im sin omega t. So this 314 is omega, and omega is 2 pi f. So 2 pi f is equals to 314. That means a frequency or f is 314 by 2 pi. What is the RMS value? As we have derived already, the RMS expression of any AC quantity. It's an AC current signal, so RMS will be always the peak current divided by root 2. Peak current is given Im, the maximum current. It is given in the equation 14.14. So 14.14 divided by root 2 will be equal to the RMS value of this AC current signal. And
Ma'am,
what
is it
will
9.99 amperes?
which one?
9.99 ampere RMS value.
Yes, IRMS, sure. Right. IRMS will be Im by root 2. It's, approximately 10 ampere. 14.14 by root 2. Considering the current signal is a pure sine wave. Fine. And frequency is 50 hertz. Because it is 314 rad per second, so it's 50 hertz. And to get the instantaneous value, what we'll do, you will just put t equals to 2 milliseconds in this expression. That means current value, instantaneous current value at t equals to 2 milliseconds will be given by 14.14 sine within bracket omega t. So 314 is omega into t, which is 2 milliseconds. Calculating this, we'll get 8.3 ampere. So 8.3 ampere is the instantaneous value of this current signal. At a particular instant, the current will be 8.3. At instant 2 millisecond, the current will be calculated as 8.3 ampere. Now look at this equation. I equals to 62.35 sine 323 t. Again an AC quantity, an AC current signal whose mathematical expression is given in the problem. What is the maximum value? Tell me what is the maximum value given in this problem?
62.35.
62.35.
62.35.
Ampere. You have to mention the unit also. What is the value of frequency here?
323 by 2 pi hertz.
Yes. What is the RMS value?
62.35
0.35
by
by
2.
root 2
Okay. Ampere. Its average value?
62.35 by
0.637
2.
into 62.35 ampere.
Average value is 0.637 into peak current. And what will be the form factor? What will be the form factor? What is the
RMS by
derivation?
average.
RMS value by average.
Okay, so RMS is already calculated as I peak by root 2. I peak is given. I peak is given. Okay. And average value will be calculated as 0.637 into the peak value of current. So we get average value as 39.69 ampere and form factor is equals to 1.11. See, it's a sinusoidal signal and alternating signal. So its form factor is always 1.11. But in case of square wave, will be only 1. Okay. See, in this problem, signal waveform is given. Okay. The mathematical equation of that signal is not given. Previously, the mathematical equation was given in the problem and you calculated these parameters. Now, the waveform is given, the signal type is given in the problem. And from the graphical representation, you can calculate the time period and the peak value only. You have to find out the RMS value and average value of this signal. Previously, we have studied how to calculate the RMS and average value of a sinusoidal signal or a periodic signal. But this is neither a periodic signal it's neither a sinusoidal signal nor a square wave signal. It is a periodic signal, but it is called a pulsed signal. So for this type of pulse signal, how to determine the RMS value and the average value? We'll see that. What is the time period? Since it's a periodic signal, we can measure the time period graphically. Can anyone tell me what is the time period given in this waveform?
T.
Capital T. So capital T is the full time period and the capital T by 2 is the half time period. How to calculate IRMS for a periodic signal? It is just equals to square root 1 by t integral 0 to t square of the AC quantity into dt. Here AC quantity is I, small I. It's the current waveform. So we'll consider I square. Fine. So for this duration 0 to t by 2, it is Im square. And for the duration t by 2 to t, it is 0. The magnitude is 0. Magnitude of current is 0. This duration t by 2 to t. Okay. So see, it's a pulse signal. So magnitude is constant for this duration 0 to t by 2. Okay. So the integration I square dt from 0 to capital T. This is the full time period. So we'll consider the full time period while we are calculating the RMS quantity. So after the calculation, after doing the integration, we are getting the mean square value as Im by root 2. IRMS is coming as Im by root 2. Okay, how to calculate the average value? It's not a sinusoidal signal. It's not a signal in which the positive half and negative halves are symmetrical, because in this signal there is no negative half. The signal is having only positive half. So here we'll apply the conventional technique for the calculation of average voltage. We'll consider total time period capital T as the upper limit of the integration. So we'll consider 1 by t integral 0 to t I dt by. So just put the mathematical expression of I, it's constant.
Ma'am, how 2 pi by t?
No, it will not be 2 pi by t. See, it is simply Im. For this duration, it is simply Im. Okay? This is not correct. Don't follow this one. Just put Im. 1 by t into Im dt. True? Is it clear to everyone? Put I equals to Im. It's a pulse signal. Like this. Okay? So this is t by 2. This is 0 and this is Im. So for the duration 0 to t by 2, it will be simply equals to Im. Fine? And for the rest half time period, the signal is 0. So we'll not consider t by 2 to t. So tell me what will be the final expression? Right?
Yes, ma'am. I am by 2.
Okay. So 0.59. So in this way, we will calculate the average and RMS value of any particular signal. It may be a periodic signal, it may be sinusoidal signal, it may be a cosine signal, it may be a triangular wave, it may be a square wave, etc. Let's see this one. This is the signal obtained by a half-wave rectifier unit, or you can say this is a half-wave rectified sine wave. Okay, if you design a rectifier unit, you can convert AC sinusoidal wave into its equivalent DC. And that DC will be a pulsating DC. So this is nothing but a pulsating DC in which the negative half cycle is absent. That's why it's called as half-wave rectified sine wave. We are going to measure the RMS value and the average value of this type of signal. How to measure? Can anyone tell me how to measure to find out average? Which formula will be used? For average value? How to calculate the average value? 1 by t integral 0 to t I dt. Fine, it's a current signal, so we'll consider the function is the current I dt. And what is the total time period of this signal given in the figure? Capital T. Capital T. Fine. So previously the signal was a pulsed signal. So easily we have considered the function I as Im. But this time it's a sine. It's a sine. So we'll consider the mathematical equation of this current signal is Im sine omega t. Is it clear to everyone? It is a half-wave rectified sine wave. It's not a pure sine wave. It's a half-wave rectified sine wave. So it's a sine waveform. So we'll consider the mathematical equation of this type of sine wave as Im sine omega t for the duration 0 to t by 2 for this half. And for the rest, t by 2 to t, for this rest half time period, the signal is 0. Okay? So for the average value calculation, we consider I average equal to 1 by t integral 0 to t I dt. What is I? I is Im sin 2 pi by t or Im sin omega t, right, into dt. And for t by 2 to t, it's 0. So only this part will be under calculation, and after the calculation, what you will get I average equal to Im by pi. For half wave rectified sine wave, average value is equals to Im by pi. And to calculate the RMS one, what you will do, you will just make the square of this quantity I. The second term will be absent because there is no signal for the duration t by 2 to t. So only the first half will be there, will be under calculation. And after doing the calculation, I RMS will be calculated as Im by 2. Im by 2. It's simply I square sine square omega t. I square will be taken as common, so it's simply sine square omega t. Make it 2 sine square omega t, and then you represent that 2 sine square theta is 1 minus cos 2 theta. That's it. Then you do the integration. Okay, next we'll move on to the main topic, that is phase angle and phase difference of alternating signals. We are dealing with alternating signals. Okay, AC circuit. So in AC circuit, these two terms are very, very important. Phase angle and phase difference. When you are analyzing two or more than two signals, definitely you need to identify those two signals with respect to their phase angles. How the two signals are related, that will be clearly understood by phase difference quantity. Now, the instantaneous value of an alternating voltage or current is different at different instants of time. That means it varies continuously with time. It is not discrete. It's a continuous signal. So at different instants, we'll get different magnitudes. That is true. But if we combine those magnitudes, we'll get a continuous signal, continuous alternating signal. Now, when two or more such alternating waveforms attain their positive or negative peak or zero values at the same instant of time, there will be a problem. Okay. What I'm trying to say, suppose in a circuit, two alternating currents are associated. This is I1, this is the signal I1, and this is another current signal, which is I2. Now this I1 and I2 are just superimposed to each other. There may be any other relationship between this I1 and I2. Now, how to differentiate these two current signals present in one circuit? How to identify the current signals? For that, this phase difference and phase angle quantities are required to understand. Right? Now, here you can see the two signals are exactly in phase. So these I1 and I2 will be called as in phase quantities. That means they are crossing the same zero instant. They are crossing the same peak instance. Suppose this is 0 and this is the total time period t, and this is the half time period t by 2. See, both the current signals are obtaining their peak values. This is the peak value. This is the peak value for I2. This is the peak value for I1. Both are attaining same zero instance, zero crossings at same instance. That means they are just in phase. Okay? Like these two signals, the two voltage signals, they are in just phase. One is marked with blue color, signal V2, and another one is marked with black color, which is V1. See, both the signals are attaining their maximum value, maximum positive peak value at the instant t by 4. Both are having same time period, capital T. That means frequency is same for the two signals. 1 by t. 1 by t is the frequency. Frequency is always 1 by time period. So here, see, it's the time periods are same, frequencies will be also same. Okay, so for this signal, the phase difference, I'm denoting this phase difference as phase d equals to 0. There is no phase difference. Look at this figure. V1 is the black colored signal, V2 is the blue colored signal. The starting points are different now. V1 has started from origin, V2 has started from the instant pi by 4. Okay? Can anyone tell me what is the frequency of the signal marked as V1 here in this figure?
2 pi.
Frequency. The time period is 2 pi, right? So what will be the frequency for the black colored signal? How to calculate?
1 by 8.
1 by 8. This is the for
Ma'am, F is equals to 1 by T.
F equals to 1 by t. That is correct. And omega is 2 pi by t. So omega is 1 here. So if omega is 1, what is frequency?
1 by 2 pi.
1 by 2 pi.
So frequency is 50 hertz here. And for the second signal V2, what is the time period? This is the starting point 5 by 4, half time period 5 pi by 4, full time period 9 pi by 4. What is the time period of the second signal?
Time period 9 pi by 4.
Is it 9 pi by 4?
No, ma'am, 2 pi.
How?
9 pi by 4 minus pi by 4.
It's 9 pi by 4 minus pi by 4. It's just 2 pi. That means both the signals are having at same frequency, 50 hertz. Fine. But one has started from 0 instant, second one has started from pi by 4. Or you can say that the second signal is lagging by pi by 4 by the first signal. That means there is a phase angle. They are not crossing the uh, zeros at the same time. See, the black color signal has crossed the zero crossing at pi by pi, and the blue colored signal is crossing the zero crossing terminal at the instant pi by 4. And also, they are not attaining their peaks at the same instant, just like the previous signal. That means there is a phase difference. What is the value of the phase difference? This difference, pi by 4 minus 0. That means V1 is ahead of some value, pi by 4 by V2, or V2 is lagging by this amount, pi by 4 by the first one. Okay, so phase difference is the difference expressed in electrical degrees of time between two signals that have the same frequency and are referred to the same point in time. The two signals V1 and V2 do not start at the same time, that is, their zero values are not coinciding in time, neither have they attained peaks at the same time. Thus, these two signals are said to be out of phase. They are not in phase, they are called as out of phase signals. Right? We can say that the signal V1 leads the signal V2 by a phase angle of pi by 4, as it is indicating that V1 has started before V2, and hence the word leading. Look at the figure, V1 is leading by V2, or alternately you can say the signal V2 lags V1 by a phase angle of pi by 4. Since V2 reaches its peak or pi by 4 zero angle after the signal V1. Okay. These two signals can only maintain a constant phase difference if their frequencies remain same all the time. That means now, as per this figure concerned, we can say that frequency is same for both these signals. So, if frequency differs somewhere after this instant, if frequency is not same, then definitely these differences will be, this phase difference will be changed, definitely, if frequency changes. So how do we express these two signals mathematically? Like, we considered the black one as the reference one, since it has started from zero instant, so we'll express this V1 as Vm sine omega t, right? And second one will be expressed as V2 equals to Vm sine omega t minus pi by 4. Since it is lagging by V1, we have taken minus sign here. If it is leading by V1, then we'll consider omega t plus pi by 4. So generally, we express any voltage equation as Vm sine omega t plus minus pi. This is the generalized equation of a voltage signal with respect to the origin. That may be leading, the signal may be leading type or lagging type. So we'll put plus minus of phi. This phi is nothing but phase angle. Okay, so these two are mathematical equation for the two signals we have used here in this waveform, and this is the generalized expression of voltage with respect to the origin or reference signal. Is it clear to everyone?
Yes.
Yes, madam.
Yes, today the class is almost over, so I'll stop here. Next day we'll start with phasor diagram. Okay, let me take your attendance quickly. Rinita,
Yes, ma'am.
Orgodip,
Present, ma'am.
Onindo,
Present, ma'am.
Oishi,
Present, ma'am.
Atul,
Present, ma'am.
Marmik,
Present, ma'am.
Marmik, Shiab, okay, Shiab,
Yes, ma'am. Yes, ma'am.
Raj, Raj, Shubhronil, okay. Next is Niladri,
Present, ma'am.
Aditya Banerjee,
Present, ma'am.
Ainjila,
Yes, ma'am.
Ovirup,
Present, ma'am.
Shori,
Present, ma'am.
Prince,
Ma'am.
Prince,
Yes, ma'am.
are you okay now?
Yes, ma'am.
Okay. Show me,
Present, ma'am.
Abir,
Present, ma'am.
Ankita,
Present, ma'am.
Shabnik Mukherjee,
Present, ma'am.
Ritu Chekar,
Present, ma'am.
Srajal,
Present, ma'am.
Kirti,
Present, ma'am.
Joel,
Present, ma'am. Present, ma'am.
Shantanu,
Yes, ma'am.
Saptam,
Present, ma'am.
Ilhan, Ilhan, Pooja,
Present, ma'am.
Aman,